Alright, welcome to section 6.4. I saw that clip on my Facebook the other day and I was utterly amazed what some people can do. Okay, they're so artistic, especially with a pancake in that instance. Anyway, let's get back to section 6.4. Today we're going to be talking about variation and modeling. This is basically a section involving trying to find some patterns or specifically looking at word problems. Okay, it's going to be a very word problem based section to help us determine what might come next in a given data set. Okay, so there's different types of variation that we're going to go over today. Let's just get started with our first one. Taking a look at this table of values, it looks like we're dealing with the number of rooms and the cost of the job. And maybe we're talking about painting so many rooms and this is how much it's going to cost us. Let's try to find some patterns within this table. As the number of rooms increases, okay, so as we go from 1 to 5, what is the total cost of the job doing? Well, we go from 20 to 40 to 60 to 80 to 100, so it looks like our job, or the cost of the job rather, is increasing as well. Let's try to be a little bit more specific though. As the number of rooms doubles, what does the total cost of the job do? So for instance, if we go from 1 room to 2 rooms, okay, we're doubling the amount of rooms that we actually paint, it looks like our cost is actually doubling as well. If we go from 2 to 4, okay, we double the number of rooms that we're painting, it looks like our cost doubles as well. So that kind of makes sense. Okay, there's some type of direct relationship between these numbers. If we take a look at the other way, maybe as we cut the number of rooms in half, okay, so for instance going from 4 to 2, kind of makes sense that our cost should be cut in half as well. And if we go from 2 to 1, again, it looks like our cost is cut in half from 40 to 20. So our total cost is halved as well. Totally making sense when we take a look at that table. But there's something a little bit more specific going on within this information. There's what's called a direct variation. There is a direct relationship between the number of rooms that we paint and the total cost that it's going to cost us. We call this direct variation specifically y is directly proportional to x. Okay, so there's this direct relationship, but when we say that, we mean this specific equation, y equals kx. Notice how it's not exactly y equals mx plus b. Okay, there's nothing on the end of this equation. It's just y equals kx. And the k is very special within all these different variations that we're going to talk about today. The k is called the constant of proportionality. So by how much is this job varying? Okay, what is that proportionality or that relationship between the number of rooms that we paint and the total cost of the job? So whenever we take a look at a direct variation, we're going to do a lot of word problems today, like I said, whenever it says it varies directly or it's a direct variation, directly proportional, anything like that, I want you to think multiplication. Okay, so that's kind of a clue or a key hint whenever we go throughout this lesson. Alright, so let's take a look at some examples of direct variations. We have y varies directly with x. So automatically we can assume y equals k times x. Okay, remember back here we said think multiplication. So we're going to take our constant of proportionality, that relationship, some numbers relating these two items together, and we're going to multiply it by our x variable. So y equals kx. If y equals -4 when x is 2, find y when x is -6. Okay, so there's kind of two parts to this. We have this first part. If this is true, then we want to do something over here. So let's just take a look at our first part. If y is -4, we can kind of put that into this general equation. It doesn't really give us that constant of proportionality. It doesn't give us that k value, but we do know that x is 2. So we know every single piece of this general equation here, which means we can figure out what k is. We can simply divide both sides by 2, and our constant of proportionality would be -2 in this case. Okay, so this is a special number that's somehow relating these two pieces together. But what we can do is now use this number to help us with this piece of information. So again, we did y equals kx. Y varies directly with x, but we just found out what k was. So we can put in -2 for k because we already found that. Okay, we did that over here. So now that we have kind of an equation that we're more used to dealing with, let's find y when x is -6. So simply plugging in -6 for x gives us a y value of 12. So we got to use some piece of information to help us first find k, that constant, but then once we have that, we can simply plug it back into our general form to help us find any other piece of information that we might need. Now, speaking of word problems, this is really used a lot in the sciences, especially physics, so I'm sure you could probably take a walk down to Mr. Jones and he'd love to talk to you about this. But let's take a look at a word problem. The force F exerted by a spring is directly proportional to the distance that it is stretched. Okay, so notice the wording's a little bit different. Over here it says y varies directly with x. The force is directly proportional to the distance. Okay, the phrasing is a little bit different, but we still are using that main idea of it's being directly related. So instead of y varies directly with x, we have the force varies directly with distance. So instead of y equals kx, we could say F equals kd by specifically using the letters they give us in the word problem. So we want to find the constant of proportionality. Okay, that's our k value. And we're going to write the equation to help us solve some specific piece of information, kind of like we did there. So find the constant of proportionality if f is 12. So we could put in 12 for f, and d is 1/3. Alright, so finding this constant, figuring out what k is, we got to move the 1/3 to the other side. We can simply multiply by the reciprocal so that these cancel. So our constant of proportionality would be a 36. So if we were to plug that back in again to our general form, okay, kind of like how we did over here, f equals 36d. So we could use this equation to help us answer any other piece of information we could possibly want to know about this specific force on this spring. Alright, so direct variation, not too bad. Let's take a look at another type of variation that we could be dealing with. This time we're taking a look at speed and the time it takes maybe for us to get somewhere. So obviously the faster we go, the less time it's going to take us to get to a particular destination. So as our time increases, or as our speed increases rather, what is happening to our time? It looks like it is decreasing. So if we double our speed, if we go from 20 kilometers per hour to 40 kilometers per hour, what's happening to the time? Well, it looks like our time is being cut in half. So, okay, so our time is halved. Now, in the other direction, what if our speed is halved? So if we go from, I don't know, 120 to 60, okay, cutting that in half, it looks like our time is actually doubled. So very different from what we had in the other scenario. This one is kind of inversely related to each other. So we would say that this is an inverse variation. So as one goes up, notice how our time, or rather our speed increased, it looks like our time decreased. Okay, there's this inverse or opposite relationship going on. So just like direct variation, we kind of have this general form or equation to help us when we have this relationship or this inverse relationship between ideas. We would say y is inversely proportional to x, so that means y equals k divided by x. We still have the same letter to represent our constant of proportionality. Okay, so this number can change depending on any scenario you're talking about, but in this case I want you to think about division. Okay, so when we were directly related, we were thinking of multiplication. Okay, so if I go back over here, for instance, notice how our k is being multiplied by the x. But when we have an inverse variation or an inverse relationship, our k is being divided by the x. So I want you to think about division. Alright, so let's check out a word problem. The note played by each pipe in a pipe organ is determined by the frequency of vibration of the air in the pipe. So how fast the air is moving within the pipe is actually affecting the note that you're playing. The fundamental frequency F of vibration of air in a pipe, in the organ pipe, is inversely proportional. Okay, so we have this division relationship, or kind of opposite relationship, to the length of the pipe. Find the fundamental frequency of a 1.6 foot pipe, so I'm going to label that as an L because we're dealing with length, if the fundamental frequency of an 8-foot pipe, so there's another length, is specifically 64 vibrations per second. So that's a frequency right there. So since we have this inverse relationship, we could set up an equation to help us answer this scenario here. We could use y equals k over x. We're going to think division because it said inversely proportional. So instead of using y's and x's like we did up here, let's use f and l's because that's what we're talking about in this scenario. The frequency varies inversely with the length. Just like y varies inversely with x, f varies inversely with L. So we could say f equals k over L. So let's use the pieces of information they give us to try to figure out what this constant is, because notice how they didn't tell us anything about a constant of variation. We do have a specific relationship, though, between these two pieces of information. We know an 8-foot pipe is going to give us a 64 vibration per second frequency. So we could put 64 in for our frequency and 8 in for our length. Multiplying both sides by 8, our k value would be 512. Okay, so that's our constant of variation. But now we can use this back into our general formula, 512 over L, to set up a general equation specifically for this scenario. Okay, so if we're dealing with another pipe organ or some other instrument, this constant of variation might change. Okay, this is the only constant for this particular example. So now let's answer the question. Find the fundamental frequency. Okay, so we're trying to find F. If we have a 1.6 foot pipe. So if that's a length, we can put that in for L. I don't know why I wrote 5 there. That should be F. F equals 512 over 1.6. So in this specific case, if we were to have a 1.6 foot pipe, we would have a frequency of 320 vibrations per second. So we can use this idea of being inversely related. Okay, there's this kind of opposite or division relationship between these two pieces, the frequency and the length of the pipe, to help us figure out any sort of piece of information we need to know about this specific scenario. Alright, so moving on to another type of variation called joint variation. This one's very similar to direct variation when we were multiplying, but joint just implies that we have more than one item. So for instance, y is jointly proportional to x and y means that a w is equal to that constant variation times x times y. So joint proportionality or variation is just dealing with multiple items. If we said w was jointly proportional to a, b, c, and d, we could have something like w equals k times a times b times c times d. Okay, so joint variation, very similar to direct where we're multiplying, but we're just dealing with more than one item. We're comparing more than one thing. So let's take a look at an example. The volume V of a right cylinder cone is jointly proportional to the square, ooh, there's something different, the square of its radius r and its height. Find the equation of variation if a cone of height 8 inches and radius 3 inches has a volume of 24 pi cubic inches. Oh my gosh, a lot to take in. But let's try to decode this. The volume jointly varies, okay, jointly proportional to the square of the radius. Okay, so that means r squared. Okay, it's not just a variable anymore, a, b, c, d, x, or y, where you need to put in some extra piece of information there, the square of the radius and its height. So if we were to set up our little general equation, we could say v equals our constant of proportionality, that k, times our radius squared times our height. Okay, we have two pieces in here because it is jointly proportional. Find the equation of variation. Okay, so that involves us trying to figure out what k is. We need to figure out what is that constant of proportionality, and they give us some information to help us figure that out. If the height is 8 inches, so we can put 8 in for our height, the radius is 3 inches, put that in for r, We need to figure out what k is, so we're going to leave that the same. But they give us a volume of 24 pi. Alright, so let's figure out what k is. Doing some simple math here, 3 squared is 9. 9 times 8 gives us 72. And if we divide both sides by 72, we'll get 24 pi over 72. Okay, that'll give us k. But we can simplify 24 over 72. That'll give us 1/3 pi. Okay, so I'm just simplifying the coefficients or the numbers out here. 24 over 72 can simplify it to 1/3 pi. So if our goal was to find the equation, v equals, okay, we're going back here. Our constant that we found was 1/3 pi. And we said that we had the radius squared and the height. So here is an equation we could use for any type of piece of information we might want to find that's related to this specific scenario. Alright, let's check out another example. The frequency f of a vibrating guitar string, okay, so very similar to the pipe organ example we already did, varies directly with the square root of tension and inversely, oh, we got another one there, and inversely proportional to the length. Okay, what is the effect on the frequency if the length is doubled and the tension is quadrupled? Okay, so multiplied by 4 in that case. So remember, back to those key words there. Okay, if it says directly proportional, we're thinking multiplication, but if it says inversely proportional, we got to think about that division. So our frequency f varies directly, so I'm going to take k times, what does it say, the square root of the tension, so I can say square root of t, but I need to divide that because it's inversely proportional to the length. Okay, so we could have some kind of combined variation going on here. We could have some pieces being multiplied where our other pieces might be divided. It depends on what the wording actually says. Directly meaning multiply, inversely meaning division. So we got to figure out what is the effect on the frequency. Okay, what's going to happen to f if the length is doubled? So let's try to figure that out here. What's going to happen if our length is doubled, meaning taking 2 times L, and the tension is quadrupled, okay, 4 times T. So we got to figure out what is the effect, what's going to happen to f if this were to happen. So we're kind of manipulating what's going on here on our guitar. What if we were to double the length of the, what does it say, length of the string, and what if we were to quadruple the tension? What's going to happen to the force? May that be with you, by the way. Okay, may the force be with you. Anyway, okay, so the square root of 4, if we start to actually simplify this, the square root of 4 is 2, which means I can have k2, but the square root of t does not simplify, so we still have that square root of t. Now, 2l, can't really do anything with that, but notice what we have here, okay? Notice how the 2's are going to cancel each other out, so what we're left with is k times the square root of t over l, but that is exactly what we started with up here. Okay, so it doesn't really matter if we double the length and quadruple the tension. Okay, both of these pieces would have to happen in order for nothing to change. So what's the effect? We could say absolutely nothing, because our general equation, this directly and inversely proportional equation we found, does not change whatsoever. So doing a little simplifying there, we can figure out, well, what's going to happen if we do certain things, if we start to experiment with this scenario. So what this is actually an example of a combined variation. Like I said, it's a situation that varies both directly and inversely. So we have two of these relationships. Notice how we had to multiply by k and divide by L. Okay, combined variation, we're literally combining both of these relationships. Alright, so what I want you to do is try these three on your own, follow the directions carefully, and I'll be back in a little bit to see how you do. Alright, let's check it out and see how you did. The electrical resistance R of a wire varies inversely, so we should be thinking about division whenever we see that, as the square of its diameter, or in other words, with the square of its diameter, D. So R varies inversely, so R is equal to the division of this constant of variation by the diameter squared. Okay, we can't forget those little key phrases there, the square or square root. It might say the cube. Okay, we gotta be careful with those. Number 2, the frequency of sound, F, varies directly, so we should be thinking multiplication of the square root of the tension, and inversely, so we need to divide by specifically the square root of the mass per length m. So F varies directly. F is equal to our constant times, okay, directly, times the square root of the tension, but inversely meaning divided by the square root of the mass. So this is our little general formula we could have for this instance. W varies jointly. Okay, so we're going to be multiplying a lot of things here, specifically x, y, and z. So we have our jointly related equation, y equals our constant k times all of these multiple things that we're comparing. If W is 36, so we can put that in for W, and X is 2, Y is 8, and Z is 12, we can figure out what our constant of variation is. We can get a K value of 0.1875. But if we know what K is, we can put it back into this general equation or formula we had from the very beginning to get an equation to answer anything we could possibly want to know. So we want to figure out what is W when X is 1, Y is 2, and Z is 4. So by simply plugging in those values, we get a Y value, a W value of 1.5. Hopefully we did really well with those. This section can get tricky, especially when we start dealing with the word problems, but you just got to look for key pieces of information. Are we dealing with inversely, maybe directly, or jointly? You got to take a look out for those squares or square roots. Okay, so you really need to decode what's going on within these word problems. Good luck on the practice and the application and the mastery check, and I'll see you guys on the flip side. Oh, speaking of flip, check out this pancake.
This is where you separate the men from the boys. Yeah. There you go. Yeah. I got you now. Happy birthday! Woo! I hope you're hungry. You should see that toast. I couldn't even get it through the door.